Hello. uh, oh, whoa. Oh, wow. Okay, I see what happened there. Hello. Okay. Hi, Maisha. Hi, John. Hi. Wow. Yeah, this is intense. Hello, Eric. Hello, Eric. Awesome, awesome. More people coming. Hi, hi. Hi, May. Um, hi, Noel. Why am I yelling? I don't know. Hi. Oh, interesting. Now I see what's happening. Okay. More people coming. Oh, good. Okay. Oh, I mean, sorry. Hello. Okay, we're gonna get rolling in a second. Hello, Lizzie. Great to see you. Or great to see you for a second. Um, oh, great to see you again. Okay. Um, and give me 1 second. Also, sorry. Okay. Okay. Good to oh, sorry. All right, I'm looking at the chat. Uh oh, hi Lizzie. Or I said okay, yes. And hello, Jayla. Great to see you. Hello, May. Oh, I see what's happening now. Okay, you guys are hilarious. Okay, but hello. If there's anyone missed, hi. Okay, that's funny. You're all getting those would count as multiplayer co-op participation points, except I haven't posted that portal yet. But when I do, your hellos to each other. You can count. I will post it soon. Also, logistically, at this point, if you've turned in a thing on the spring, excuse me. Okay. If you've turned in a thing on a spring, yay, thank you. Acknowledged, great. You have not gotten it back yet. That's on me, not you. Like none of them have come back yet. Um, so you can still turn it in. You can still do revisions. You'll note we don't have new homework due Monday. Like we're going to stay on a thing on a spring for a little while. I've mentioned it's a very big, it's actually a bigger assignment than it looks like. It contains all these different things that we need for the rest of the course. So we stay on it for a while. So, and I'll check in a minute, but I think all of you actually have, just about all of you have made an attempt at it. So great. As far as the game turns, this is our fourth class. There have been 3 assigned so far and 1 more assigned for tonight. I believe that all of you have got, anybody who's done the first 2 should have gotten them back. I mean, they're obviously very quick. I don't mean to, but hopefully if you did game turn 1 and or game turn 2, I believe you got them back and we both know the system's working. Game turn 3, most of you turned in, thank you, but they haven't come back yet. I'm just, so hopefully if you turned in game turn 1 and or 2 and you didn't get it back, please let me know in direct chat or whatever. And again, if you turned in thing on a spring, but you didn't get it back, I know that. Other logistical things. So we're going to start in a second, getting back to thing on a spring. We're going to get back to thing on a spring again in a second. Oh, also you should have found, hopefully now that we're starting to get into the material, the PDF of notes from anything we do from the last couple of classes, you should see in your Google Classroom, like the PDF of notes from class number 2 and class number 3 or whatever. And hopefully you're seeing that these classes are starting to go on YouTube. Like, of course, the first class was not recorded at all, but the first material class should be up there on YouTube. The second class, which is last time. So I think the YouTubes have now caught up, so to speak. I don't think you probably need them yet, but if they're not there, let me know. Okay, more people are coming. Okay. So we are starting a second. There was one other logistical thing I just wanted to address. Right. It just confirm. So my understanding, your lab is generally supposed to be run by Professor H. Walters. I know it was online last week and correct me if I'm wrong, but I believe you're in the section. I believe you have lab generally on Fridays at 3:05 with Professor H. Walters. I believe, no, not you. Oh, weird. Oh my God. Oh my God, you guys are out of control. I believe you had, when yesterday was a Friday, and I believe you did have lab online yesterday. That was for the last time, like just to confirm or repeat, starting, of course, we don't have school this Friday, but a week from this Friday, you should be back in the actual lab. Please, unless you hear otherwise, please do go to John Jay to the third floor to 0365 for physical in-person labs starting a week from this Friday. But I believe yesterday was online, and I believe yesterday you actually, if I'm not mistaken, you actually did have Professor Walters herself, I believe, zooming in with you. Is that correct? Yes. Okay, great. But you were, huh. Okay, I'm not going to go down that road, but okay, cool. Okay, but yes, so yeah, all right, cool. Thank you. Thank you, Alea. Thank you, Lizzie. Thank you, John. Thank you, May. Thank you, Jayla. So as of next Friday, you'll again, please go in person. There might be a slight alteration, but anyway, it'll be in person next Friday. Okay, so that's all the logistics. Now, I want to get back to Thing on a Spring. Start moving a little bit faster through it now. Again, we're using it as a model to how to do the 5-step method of turning in homework. But we're starting to try to get some answers now. So I believe, correct me if I'm wrong, but I believe we got up through just question 1 last time. I believe we're now on question 2. So let me know if I'm wrong. So here, right. So here's question 2. Oh yeah, and so notice, just technical point, notice I write at the beginning, for diagram and fact pattern, please see above. By above, I mean your earlier notes or the beginning of your homework from Monday. So I'm just still trying to pretend that I'm you or student. What I would do to turn in, like we always want to do DFP diagram and fact pattern first, but it is the same diagram and fact pattern for this entire problem. So it's totally advisable to just write that. And please do, so I wrote, please see fact pattern from above, and please do so for all remaining questions. So from here on in, I'm not going to keep repeating the DFP for every one of these questions because it's the same DFP for everyone, but there it is, that's DFP. Also, again, I'm not ever saying that you guys have to write out literally DFP or step 2 WIQ. I'm not saying that, but I'm saying track it in your head. Make sure you're doing all these steps. And if we ever write to you WIQ or DFP, you know what it means. Oh, okay. Oh my God. I'm making the mistake of reading the chat, which I should never do in this class, but okay. So then up to WIQ, step number 2, the question for question 2 is at t = 0, what is A? Now I'm saying note. That actually says note. I can't read my own handwriting. Hold on a second. That's meant to say note. Hold on. Okay, it's asking us. Yes, I am. Yeah, poor prof. That's funny. Oh, Jayla. So we're solving for A, for acceleration here, but notice it does not have a bar over the A. We're solving for instantaneous acceleration at a point in time and space, specifically the point in time t = 0, or in other words, the point in space where x equals positive 0.15 meters. So notice that like instantaneous acceleration is not the same thing as average acceleration. So for example, we're not going to use any equation that has to do with average acceleration here. And the question sort of does imply that whatever acceleration we get for this answer may not continue to be the same answer for the future questions, that's just like a side note. Okay, so how do we do it? Well, so that's the question though, solve for A. So I go to step 3, GDP, general definitions and principles, and the general definition and principle or law or whatever I want here is Newton's second law, F net equals ma. Now F net equals ma, the sum of all forces on an object equals ma. But I should actually note here. Yeah, so Zhao Wei's question, I'm saying notice that instantaneous acceleration does not mean the same thing as average acceleration. Or put another way, I'm saying they don't mean the same thing. So any equations that you might have or might be thinking of that have to do with average acceleration, we would not want to rely on here. Or put another way, I'm saying that okay. John's point is a good one. I'm going to get to John's thing in a second. But yeah, so I'm just saying here, note the acceleration is not a constant. It's different at every instant. So when we're solving for instantaneous acceleration, we really are trying to get a value that is true at a particular point. That's all what I'm saying to Zhao Wei. I don't know if that helps or not. Then before I get to John's question in the chat, and there's something else in the chat, but before I get to that, I just also want to note slight technicality, but it's not really a technicality. It can often make a very, very important difference. Newton's second law, reminding you from physics 203, Newton's second law is net force equals mass times acceleration, i.e. the sum of all forces acting on an object produces the acceleration of that object. So no one individual force necessarily ever produces acceleration. All the forces together on a given axis of space produce the acceleration. Here, however, there is only one force acting on the x-axis. That force is the spring force. So whatever we got for the spring force, we are going to substitute in or plug in for net force, but that's because there's only one force acting. I just want to do a general shout out or general emphasis of don't think in general that net force and force mean the same thing. Net force means sum of all the forces. Now, let me just note in the chat, something's happening in the chat. So yes, to Zhao Wei, to Zhao Wei, yes, that's what I'm saying, that the acceleration is not constant. That's right. That's good. Thank you. And then to John, I think I agree. Oh, yeah. Oh, good. I see what he's doing. Right. And I'll do that on the next page. But yeah, John is paying attention to units, which thank you. That's good. This is a science class, not a math class. Absolutely paying attention to units. So indeed, 1 Newton of force does equal 1 kilogram of mass times 1 meter per second squared of acceleration. Absolutely true. So yes, when I solve on the next page, the units had better work out. And indeed, yes, the kilograms will cancel out and will end up in meters per second squared. So I totally agree with John. So notice quick, again, for people just getting used to this method. So I wrote F net equals MA, like Newton's second law, as my step 3, general definition of principle. It's a law. It's almost like a triple equal sign, even though technically it's not. And now I go to step 4, particular application and work. Now I'm starting to apply to the specific circumstances of this problem. I'm plugging in the particular value. So the particular force, the spring force here, we already solved from question 1 is negative 30 newtons. That's above. The mass is 0.3 kilograms. That's from the given in the problem. So I go to the next page, and excuse me, I'm just turning on a light. Okay. So sorry. So now I'm on the next page. So now I'm solving for the particular acceleration, and I'm going to pause here. So you see, so I did step 5. Did I forget to write it? Maybe I forgot. Oh, no, yeah. Step 5 is final answer circled. And there it is, instantaneous acceleration. I should actually even say, to be really specific, I'm sorry, I should say at t equals 0, a equals negative 100 meters per second squared. Now, let's pause for a second. I want to make a couple of comments on this answer. Like, things are starting to get a little bit more physicsy now, right? Like, I want to say a couple of things. One is I definitely want to address a really good question that's in the chat, or there may be more than one question in the chat. Let me see. The KG will cancel out any fantasy. Okay, that's fine. Oh, yes. Okay. North Hall. Well, I don't know about North Hall, but yeah, the back. Right. Okay. The background is totally John Jay. Yeah, actually, that's a view from my office. If I ever go back there again, uh, that's taken through the window of my office on the fourth floor. So yes, that uh let's not maybe okay, but wait okay, wait. So no, I'm sorry. My technical actual office is on the fifth floor, but I almost never go there. My research lab is on the fourth floor, and that's what I really actually kind of use as my office. I mean, it's a very small lab, and it's there right there on the fourth floor, right near the Jaywalk. And I'm there on Tuesdays. But okay, but I want to get to Stephanie's question. Stephanie's question, and in fact, to be honest, I think even also Maisha and some other people even asked me about this negative sign in the last couple of days. I want to address this and a couple other things about this answer. So first of all, yes, A can totally be negative, and F can be negative. And in fact, I mean, this is from, it can be, and in this case, it really should be. Let's remember from physics 203 that negative, when it comes to acceleration, well, when it comes to anything, negative means direction. A negative acceleration means accelerating in the negative direction. That doesn't necessarily mean slow down. A negative acceleration either means, a negative acceleration either means that you're moving in the positive direction, slowing down, or you're moving in the negative direction, speeding up. Like remember, acceleration is change in velocity per time. So a negative acceleration means that your velocity numbers are getting smaller and smaller. So that could mean, and velocities are either positive or negative. Your velocity is positive in this case if you're moving to the right, and your velocity is negative at any moment if you're moving to the left. So your velocity, so this acceleration, this negative acceleration means that you are losing velocity. That could mean, in general, that could mean like your velocity is going from like positive 500 to positive 400 to positive 300, et cetera. Like then your velocities would be getting lower, right? Like if you were moving to the right, slowing down, or it could mean, as it does here, it could mean your velocity numbers are getting more and more negative. They're getting lower and lower because you have negative velocities that are getting increasingly negative. And frankly, that's what's happening here. Like your velocities are doing something more like negative 100 to negative 200 to negative 300 or something. Like we'll see the numbers in a moment. But I'm saying your velocities are negative because you're moving to the left here, and they're increasing in magnitude by 100 meters per second every second. So what I'm really saying is, first of all, yes, acceleration can be negative. Two, that doesn't necessarily mean a slowdown. Three, in this case, your acceleration really should be negative, and in this case, it does not mean a slowdown. It's a speed up in the negative direction. Now, you might ask, and some people did ask, like in texts and stuff over the weekend or over the week, some people said, is it okay if my acceleration here is positive? Well, it's okay only if you've chosen that coordinate system. Like, sure, everything is negative and positive based on your coordinate system, based on what you assigned to be the positive and negative directions on your x-axis. And yes, that is up to you, but you have to make some kind of choice and you have to be consistent with it. So, okay, so this acceleration could be positive if and only if you chose to make the rightward direction in your coordinate system negative. And that means if this is positive, if and only if you called that initial position of the mass, that initial displacement from equilibrium, if you called that negative 0.15 meters, then okay, this is positive. But honestly, I don't think most of us did that. And I don't think it's a very productive or wise thing to do. It's going to give you more negative signs than you really want. So I want to make it clear, this thing is accelerating to the left and speeding up. And I want to know that going for the rest of the problem. So honestly, my answer really is negative 100 meters per second squared. And I'm not saying if you did everything right and you got that wrong and I'm not saying you'd lose tons of points or something, but I am saying like that is the correct answer. Last thing, and then I'll look in the, well, actually, let me look at the chat. Yeah. Correct. What John? Wait. We just talked. Okay. Yeah, I research physics, but we could talk about my research. Right now, I research COVID. I mean, who does? I mean, I don't really, but right now I don't do anything. I'm just trying to get through the day. But on John Ford's like more serious physics point here, yes, it's negative because the thing is move. It's negative because negative means left, or on the page means left. Negative means toward equilibrium. Negative means left, and this thing is accelerating left, meaning it is moving left and speeding up. So yes, like what John Ford said, yeah. Or put one last final way, the acceleration is negative because the force is negative. And the force is negative because yes, it is pulling against the direction of original initial displacement. The force is toward equilibrium, toward zero. So yes, wait. Yes. So John's thing in the chat, any negatives throughout this whole problem, and this is true in life, negatives in physics always mean direction, and they always mean direction based on how you've assigned or set up your coordinate system. So yes, totally yes. Okay. So that's so that's the answer to that question too. Now let me say one more thing, especially maybe either for people who don't know me or notice one stylistic choice that I've made in doing the work, a choice that you might not have made in your work. And I'm not saying you'd lose points quite yet, but I really want to encourage it. Notice, like I wrote down F net equals MA on the prior page, but I'm solving for A, right? So before I plugged in numbers, I rearranged the equation to isolate A. This is a minor, I mean, it's not minor, this is a subtle stylistic point, but I want to bring it to your attention, especially if you're trying to get good at physics or better at physics or whatever. Notice I made the choice in doing my work to algebraically rearrange F net equals MA and say, okay, therefore A equals F net over M. Then I plugged in the numbers for F net or for F. Well, in this case, in fact, I'll even say, in this case, it's F. Right, the net force was the force. Okay, so I rearranged, and then at the last possible minute or the last possible step, I then plugged in the numbers and solved. I've mentioned this before to some people in Physics 203, but I really want to emphasize it now, especially in Physics 204. Really try to get into that habit. I know that many of you can plug in the numbers even before you rearrange, and you can see how to do it and you can get an answer. And I know many of you are probably in the habit of doing that and probably think that you prefer. Many of you may prefer to plug in numbers as soon as you can and then do whatever rearrangement. I want to tell you that that's a habit you want to sort of try to grow yourselves out of as we get into Physics 204, because more and more this physics is going to look like math. And I mean math, I mean like calculus or trigonometry and stuff like that. And more, we're going to have fewer and fewer numbers in this course as we go. It's going to just look like generalized, abstracted mathematics, like what you consider physics to look like. And we really want to be in the habit of being able to follow and understand and work with these equations with no numbers at all. I'm not saying that's easy. For all of us, it's more concrete and easy to picture what's going on when we have the numbers in there. But the numbers are going to disappear from our lives. So this is a good time, a good opportunity to really start getting yourself in the habit of being able to just do the generalized algebra without the numbers. Also, please note, as I've mentioned to people before, the fact of the matter is that the algebra is true. It's just true, whether or not you've correctly copied or correctly followed or correctly gotten the numbers for this particular situation. So the longer you can postpone anything that's just happens to be true for the situation, the more points you're accumulating, the more you can keep things as general truths, the more they're just generally correct and they're right, and they point you toward the path of finishing and solving the problem, but leave the particular numerical details of a problem for as long as you can, is what I'm saying. But all right, that's just advice, whatever. All right, so that's the answer to that one. Negative 100 meters per second squared. Okay, then we go to question 3. Next question on the sheet. We go to question 3. So now it says at x equals 0. At x equals 0, what is A? A moment ago, we did when t was 0, what is A? Now we're doing when x is 0, what is A? Or put another way, a moment ago, we did when x is 0.15 meters, what is A? Now we're doing when x is 0, what is A? So again, this totally implies this question. I mean, it very much assumes that A is not remaining the same throughout. And I don't think it is, because A comes from F, Newton's second law, F not equals ma. The acceleration is determined by the force, and the whole point of the spring, whether you knew it before last week or you know it now, the whole point of a spring is that it exerts a different force at every different position. The whole point of a spring is that it introduces us to, the whole point of a spring is that it's a vivid, central, fundamental example of a force that varies as a function of position. So if the force is varying, the A is varying. The A is not constant. We're now asking for an A at a different spot. So we're going to do the same procedure for sure, the same GDP, F net equals MA, okay, and F equals negative KX, you see on the bottom of the sheet. I'm just repeating from before. But here now we're solving for where X is 0. So we're solving for where F is, so we're solving for where X is 0, so F is 0. Put another way, when the spring is relaxed, when the spring is at equilibrium, it doesn't have, it's already restored. It doesn't have to exert any restoring force. And mathematically, you plug in 0 for X, you get out 0 for F. And then F net equals MA. So the point is, at that spot, at the equilibrium spot, the mass is not accelerating at all. It has been accelerating, and it will be accelerating again, but instantaneously, right now, the mass has 0 acceleration. Right, okay, so stop me if you don't want me to go on. But so I think that's the answer for question 3. So now I'm going to question 4 on the page, as you see. Question 4, at x equals 0, what's V? Now, what's and for the record, if you read the English of the problem, I believe that technically, and stop me if I'm wrong, but I think the question actually asks for instantaneous speed. It doesn't actually ask for instantaneous velocity. That doesn't mean we couldn't solve for it, but it's only asking for instantaneous speed, meaning the main focus of this question is just to find out how fast the thing is going. I'll tell you right now, like at equilibrium, the thing is still moving to the left. So if we were talking about velocity now, it's going to be a negative velocity. The question's not concerned with that. So it's just asking for speed. We want, well, yeah, right. Yeah. So I'm agreeing with what John put in the chat. And I do the same. You're going to see I do the same thing on the page. I'm solving for V. Technically, usually V stands for velocity. Technically, what we're solving for here really is like the magnitude of the V vector. But yes, I use V as well. I just want to make it clear that even though in the earlier questions we were kind of stressing about negative signs, for this question, we're not even going to stress about negative signs. I'm just saying that, but yes, that's totally okay. Okay, so no, wait, so it's right, exactly what John said in the chat. Because I'm asking for speed, the answer I'm going to get is going to be positive. It is true that had I asked for velocity, then whatever answer we get here really ought to be negative. But yes, so I'm agreeing with what John's saying in the chat. Now, so I'm going to solve for V now. Now note, again, this question implies something that you might not have thought of before, or you might not like. This question implies that the answer is not 0. And it isn't 0. We're going to look for a non-zero answer here. The velocity, the speed of the object initially at the very first spot was 0. But we just learned that the object is accelerating from the get-go. It's speeding up. as it comes in from 15 centimeters. It's building up speed as it comes in. So by the time it gets to equilibrium, it's going to have a bunch of speed, a non-zero speed, and that's what we're solving for here. So you might think, so I really want to address this, because for some of us, we might either consciously or unconsciously be thinking, well, wait a second. I mean, some of it, including me, I once upon a time thought, well, wait, I mean, we're asking for the speed at equilibrium. I mean, isn't that equilibrium? So shouldn't the speed be zero? That's not an unreasonable or crazy thing to think. Like, in fact, it's a very thoughtful thing to think, but it is wrong. And here's why. We want to know for the future, like, equilibrium sounds like a place of rest. It sounds like a place where things are at rest. That's not actually what equilibrium means in physics or in science in general. What equilibrium, so here's the definition of equilibrium. There's like a little sidebar here just to justify the question. But what equilibrium really means is a place where the forces are in balance. I mean, equilibrium means balance. What's in balance in equilibrium? All forces, i.e. a spot of equilibrium is a spot where net force equals zero. Therefore, by definition, always what you can rely on is an equilibrium position is a position where the instantaneous acceleration is zero. By definition, yes, equilibrium does mean A equals zero. That like is always going to be true, but it doesn't mean that V equals zero. It definitely does not mean that. You could be at rest at equilibrium, but you don't have to be. The reason people often think, unconsciously or not, the reason that people often think, oh, equilibrium, thing must be at rest, is that equilibrium is the one spot for which, if you place something at equilibrium, if you put something at equilibrium and make it at rest, and then let it go, oh, then it will stay at rest. Yes, because acceleration at equilibrium is zero. So changes in velocity are zero. So see, anywhere else in a spring, anywhere else, if you place something there, like 15 centimeters, like our problem here, we place something at 15 centimeters, we hold it there, it's at rest. But if we let it go, now it starts to move, right? It doesn't maintain a velocity of zero. But equilibrium is the one spot that, yes, if it starts at velocity zero, it will maintain that, because what's true definitively is that acceleration is zero. Conversely, however, now to bring us back to the problem, if something happens to be coming toward equilibrium, like here, things are moving toward equilibrium, the restoring forces are pulling the mass toward equilibrium, then by the time it gets to equilibrium, it's moving. It is moving. It's going to keep moving. It cannot stop on a dime. It cannot accelerate at an infinite rate. It can't lose all of its velocity in no time. So when this object gets to equilibrium, it will get there with some speed. And what I predict and what I want you to visualize is it's going to keep going into the negative region of the x-axis, which is really why we really have to care about positives and negatives. When I let this thing go from positive 15 centimeters, it's going to move to the left, toward equilibrium. It's going to keep going through equilibrium into the negative positions. And I predict, we'll find out, I expect that it's going to keep going all the way to negative 0.15. Like, I haven't proven that yet, but I think you might join me in guessing that, assuming that this is an ideal spring. And while it's doing that, while it's moving in the negative displacements, the force will now be pulling it back toward equilibrium. So the force is always negative of the displacement. Even if the displacement is negative, then the force will be positive, if you follow me, right? But that's how the negative signs work. And last thing, assuming that this is a well-behaved spring, assuming this spring obeys Hooke's law, then I expect it's just as capable of compression as it is of extension. If it's capable of extending Right. That's funny. You really are paying attention. Yeah, I used to always hate that expression too. Right. Yes, the spring is a very good boy. It's very well behaved, which is a funny expression. But that is a physics math expression. It really means if it's obeying the law to the full extent of the law, the physics law, not the police law. So, what was I saying? Oh, yeah. So I do, if someone says this is a well-behaved spring, it's a Hooke's law spring, then they mean whatever extension it could possibly be subjected to, it can also be subjected to an equal amount of compression. So I believe this spring is capable of bringing the mass from positive 0.15 all the way to negative 0.15. And I actually believe that that's what's going to happen. We're going to find. But so, and once the mass is in the negative zone of positions of displacements, it will have positive pointing forces and accelerations. I hope that makes some sense. Now, I still haven't answered the question. I've been babbling and babbling and babbling. What else is new about this question? But I haven't answered it yet. And honestly, and I'm about to now, or at least about to start. But one of the reasons I think I'm babbling a lot about this question is this: now the physics is starting to get a little bit more involved here. Like, this question is asking me to get an instantaneous speed at the equilibrium position. I think this is the first question on the sheet that I don't think any of us can just like do in our head. I mean, maybe you can, but I don't think that, I mean, maybe it's a plug and chug, but it's a little bit more involved than the prior questions. I will say, I do believe if you're going crazy with suspense or whatever, I do believe the answer to this question is going to be approximately 3.87 meters per second. If you got that, then good, then you're with me. Please don't leave. But yes, but I want to talk about, but I think many of you may either not know where I got that, or you might have sort of gotten enough off the web in order to get it, but you may not really know why what you got from the web worked or why. So we're now starting to get in the realm of stuff I want to start developing. So here's the deal with this question. Right. So back to this question now. The first thing I want to say, let me look in the chat. There's something on the chat. Oh yeah, he's good. Okay. So now I'm solving question 3 here. First thing I'm saying to you as a class, and the first thing that somehow maybe quickly or concisely you might even want to jot down in your answer if this were homework or a test, is we cannot use kinematics equations here. We can't use the one-dimensional constant acceleration equations that all of us spent a long time developing in physics 203, whatever class you were in. Now, let me be very clear about this. I'm not saying those equations are wrong. And in fact, I'm not even, if you wrote one of those equations down right now, you get points for it because they're true equations and they're not going away. I mean, they're still with us for the rest of our lives. They're correct, but they won't help us here. And this goes back now to what Zhao Wei was saying in the chat. Like, those equations, again, if you wrote one down, you get points because it's true. It's a general definition and a principle that's true. But we're going to have to go a step farther and notice that well, I guess I'm getting ahead of it, that what we said, I don't even know if you can read my handwriting, but we said that those are constant acceleration equations. They look good. They look like they relate A to V and X, which looks like the information that we're dealing with here. But they all assume, that we have some, excuse me. They all assume that we have some constant value for A, which we don't here. A is changing at every point in time and space, excuse me. So we can't use those equations. That itself is information, okay? I'm not saying you have to write all the stuff that I wrote right here, but if you even wrote those equations down on homework or on a test, and then you went an extra step of saying, they will not apply here because and I'll get the chat in 1 second. If you actually go the extra step of saying they do not apply here because acceleration is not constant here. They do not apply here because acceleration varies. Why? Because force varies. Why? F equals negative kx. That means for every different x, there's a different F and therefore a different A. That is the reason that those equations don't apply. And even writing that down, that is a true and important observation for which you would get points if you wrote it down. I'm going to look in the chat at John's thing in 1 second. but I want to be really clear about this, especially for exams or whatever. Like, many of us might have gotten stuck at this moment, unless we went on the web or something like that. Or some of us, I might have been smart enough to realize, okay, my A equations are not going to work here. Then I might have been the kind of person who goes, wait, the A equals like V squared over V is not going to work because this is not constant acceleration. Darn it, I have no idea. I don't know what to do. Like, I'm not saying you all said that, but like that can happen. I wanted to say, if you think you have no idea here, you definitely do have an idea. Like, nobody has no idea here. The person who's closest to having no idea is the person who just totally thinks they can use these equations. And that would be wrong. But even that's an idea. It's just a wrong idea. So in other words, the person who doesn't know, who doesn't see what I'm saying, might have written those equations down, plugged in an X, plugged in an A, and gotten a V, and they get the wrong answer. And if it were an exam, they lose some points on the answer. But they would have done a bunch of stuff. They wouldn't be frustrated. They would just be wrong. And that's the end of that. The person who knows a little bit more, this is like a little knowledge is a dangerous thing. The person that knows just enough to know that those equations won't work here, they know a little bit more than the person who doesn't know that. But the odd thing about physics, or the sort of frustrating thing about school, is that if you know just enough to know that those equations won't work, you might then suddenly get frustrated because you're like, I know they won't work, so I don't know what works. So I have no idea. Right? I mean, all this would happen in the brain very fast and unconsciously. I'm not criticizing anybody, but I'm trying to like pull you along and say, if you get to that point right now where you're like, I have no idea, please realize you only don't have no idea. I mean, you only have no idea because you totally do have an idea, because you know what is wrong. Therefore, you think you don't know what is right. But how do you get there? You write down the thing that is wrong and why it's wrong, because first of all, you'll get points. But second of all, it's going to lead you better to what actually is right than just going like, I have no idea. What I'm saying right here, and then I will pause. I know that John's in the chat or someone's in the chat, and I will check in a second. But what I'm saying right here is the reason that we can't use, we have to stop using like the force and acceleration equations now. Like, we use them for the first 3 questions, great. Now they're not going to help us anymore. But that's not a brick wall. The reason they're not going to help us is now we're at a point where we realize, oh, darn it, force is varying as a function of position. That is the problem. That is why constant acceleration equations won't work. So if that's the problem, that force is varying as a function of position, then that means we turn to the topic or the subtopic or the chapter or the formalism that we have for exactly that purpose. I'm going to tell you now, I'm going to pause and look in the chat, that there's this concept called work and this associated concept called energy that we developed precisely to deal with situations where the force varies as a function of position. You may have seen it with your instructor before, you may not have, depending on who your instructor is. We're going to deal with it, or you may have found it on the web, but not really know what you found. We're going to deal with it now. But I'm going to tell you that, but that's the thing we need. We need something that deals with force varying as a function of position. That thing is called work. We're going to develop it now. Let me just look in the chat because something happened in the chat. Oh, great question. For all spring and pendulum, so John, great question. So John wrote, are these equations useless for all spring and pendulum problems? The one-dimensional constant acceleration equations are pretty, useless. Sorry, are they useless? Yeah, that word is so strong, but like, I don't want you to forget those equations or forget those concepts, but yes, for springs and pendulums, which are right, they're not applicable. That is right. For springs and pendulums, the point of springs and pendulums, and you're right to throw in pendulums, maybe because you're already up to lab 2, I don't know, but yes, for springs and pendulums, the whole deal is that force varies as a function of position. So we need something more. So therefore acceleration is not constant, and that is like what we're focused on now. So we need something more than those equations. So yes, good point, John. So what we need is this thing called work. Now, on this page, here's what we're going to do in the interest, even though we are making tracks here, we still have more time, but and we seem to be a little bit ahead of the other section now. Oh my God, I didn't say that. Did I say that? So here's what I'm going to say. Because again, I know people are coming from different classes, from different memory banks. So we're going to ask now, like, this is one way of doing the solution to question 4. It's my way. It is not necessarily the way you guys did it, whether you got it right or wrong. It's not necessarily the only way. But I want you to copy this down. I want you to see that ultimately I got the answer 3.87. So you might have done a different thing. And as long as it's consistent with what I'm doing, if you got 3.87, then we're on a similar page. I want you to copy this down first because I'm going to back up and start explaining it to everybody my way. Again, for some of you, this may be the first time you've ever seen this or heard about this. For others of you, you may have gotten an introduction to it before, but this is now, whether it's a refresher or review, it's also like the way we want to think about it going forward for this class. To be really honest or really clear, what I'm really saying is when we're going to start actually caring about integrals and stuff like that in this class, you may or may not have thought of this as in an integral way before, but I want to think about it that way now. So first of all, just, if you don't mind, just sort of copy this for a minute, and then I'm going to talk about what it's saying on the next page. But if nothing else, I just want to get this far. So I'm going to pause it, copy this, and also you'll see what questions you might or might not have about it, but I'm going to talk about it, but just copy this. So this is question 4. And what I'm saying is we're using work and energy. I'm going to pause for a second. And pardon me for 1 minute. There's something weird. Pardon me for. So we're going to talk about this in 1 second. Maybe if you have any questions, jot them down. For I just something weird is happening. Pardon me for one. Okay, I don't know why. Okay. Um, okay. All right. I want to talk you through this a little bit. So again, there's more than one ways to solve this, but no matter. Oh, and the way you're reading this, I'm saying it's like in columns, like you read all the way down the black and then you go over to that brown column is the continuation. I did it all on one page just to make sure we're all on the same page. The first, I think the first thing I want to say is, in light of like our whole idea that we always go to step 2 is what is the question, and then step 3 is always general definitions and principles, like things that are true, then we start applying to the particular problem. So I want to say there's more than one way that you might have solved this, or certainly there's more than one way that your work might look. That's fine. But number one, what I want to say right now is, no matter what, in order to get this question correct, in order to get the answer to this question, 3.87 meters per second, you had to somehow use the concept of work and or the concept of energy. There's no way to do this with just forces or kinematics. Like we've already established that, but somehow your concepts have to be work and energy. And again, that's the concepts that I sort of want to explain my way right now. But the second thing is that by the time you get to step 4, I mean, particular application in work, you would have work, no matter what, how you thought of it, you would probably have work that would look pretty much like the brown right-hand column of my sheet here. Like at some point, anybody who got this question right probably wrote something like 1f(kx) squared equals 1f(mv) squared. And then, and then they solved. And that's correct. But I do want to make it clear that you can't just start off by saying 1f(kx) squared equals 1f(mv) squared. That you cannot do. That cannot be the first line of your work, no matter what method you're doing, no matter who you are. The reason for that is not a principle. Like, I'm going to try to slowly talk through the black stuff so that we can see one way of getting to the statement 1f(kx) squared equals 1f(mv) squared. And I'm going to talk about it in terms of work and kinetic energy right now. For sure, there's another way to get to that, which is to talk about kinetic energy and potential energy. And I will do that as well, probably next class. So I think what I'm saying is, you could think of this in terms of work is the transfer of kinetic energy, or you could think of this as changes in potential energy being related to changes in kinetic energy. Or you cannot know what I'm talking about at all right now because you've never seen it. You're going to hear soon. But no matter what, you cannot just write 1f(kx) squared equals 1f(mv) squared, even if you think you got that from the web somewhere. That statement in itself doesn't mean anything. It's not a general truth. So even those of you who kind of do know what's going on or whatever, if you started with that line 1f(kx) squared equals 1f(mv) squared, I'm still going to, don't beat yourself up or anything, but I'm going to ask you to pay attention to what I'm about to say, because I want us all to know where that's coming from and why it happens to be true here. One last note of caution. In fact, let me say, in case I'm losing, the answer to this one is 3.87. The answer to the very next question, I'm just going to tell you right now, if you're paying attention, the answer to the very next question, question 5, is going to be approximately 0.095 meters. Why am I saying that right now? Like, I don't mean to be confusing, but I'm saying I want you to know that the next question, you're going to also use the methods of work and energy to solve it. Okay, So I appreciate John Ford's honesty in the chat, but I guess what I'm saying to everybody right now is, well, wait. No, I don't know. Wait. Okay. We should not round. I'm not going to round 3.87 to 3. I'm going to leave it as 3.87. That would be a very big rounding. In fact, if I was going to round to one significant digit, I'd probably round to 4, not to 3. But no, we're going to keep 3.87 as 3.87. No. The 3 is no. Wait. Okay, we're getting ahead of ourselves. I'm totally psyched that you watched the video, and I believe you, and that's great. And I don't want to confuse other people right now, but it wasn't that I was rounding 3.87 to 3. The 3 that comes into play, and I will talk about, I don't want to confuse anybody, but these are great questions, John and everybody else. The 3 that comes into play, well, it confuses me. It'll never, well, I'll just finish one because it's a valid point. And I'm also just trying to keep everybody engaged because I know that everybody is at different levels. Like 3, the number 3 comes into play in the next question because the next question asks, at what position? Well, right. No, you're not dumb. This is totally valid, but you are right that that's wrong. Yes. In the very next, okay, here's why I'm saying this to everybody. In the very next question, I ask a very similar question to this, very similar. I ask, like here I'm asking, what is the instantaneous speed at a certain position? In the very next question, I ask the flip of that. I ask, what position will we find this thing when it has a certain instantaneous speed? It literally is the same type of question, just inverted the information. And in the very next question, I happen to ask, what will be the position? At what position will we find this thing when it has an instantaneous speed of 3? So it is true. That's where 3 comes into the next question. It's not because I'm rounding the 3.87. But listen, but the reason I'm bringing this all up, John's not crazy. Well, John is actually kind of crazy, but not, I mean, in a good way. But no, what John's like inputting right now is totally legitimate to everybody for 2 reasons. One, first of all, just know that's pretty cool. Like John got stuck on the homework and then watched old videos from an old class. That's pretty cool and resourceful. That makes me feel like, I mean, that's always a thing you guys can do. That's great, I think. Number one. But number 2, the reason I'm alluding to the next question right now, even though we're still in the middle of this one, is because I want everybody to see, because I know from experience that what a lot of people will do with this question is either, whether it's from their past experience or from the web or something, they'll write down 1f(kx) squared equals 1f mv squared for this question. And it is true that eventually that is true for this question, but it's not a general truth. It's something that ends up being true for this question, right? And it is derived from a fundamental principle. The fundamental principle is the very same principle that we're going to use for the next question, because indeed the same type of question is being asked both times. The fundamental principle is what you want to use both times. But the fundamental principle is more fundamental than 1f(kx) squared equals 1f mv squared. In other words, from past experience, I'm just warning you that if you grab from the web or you start believing that there's some equation called 1f(kx) squared equals 1f mv squared, and you write and you see that it works for this one, and then you just blindly write that down again for the next one because the next one looks like a similar thing, like given v what's x or given x what's v, you will be wrong on the next question. You'll in fact probably get an answer like 0.113 or something like that for the next question, or maybe it is 0.005 what John said. So just warning, I want to now try to, in the 16 minutes that we have, I want to try to explain sort of where 1f(kx) squared and 1f mv squared come from. I would like us to be on the same page with that. I'm explaining it starting now. So if you've never seen it before, you'll now know. And if you have seen it before, hopefully you can see it this way. Okay, so here we go. I am saying we have F net equals ma in our life. We have this whole idea of forces related to acceleration. And that in principle is enough to solve all the rest of physics for the rest of our lives. However, physics gets a little bit difficult because F force can change from spot to spot in a given physics situation, and such as with a spring. A spring is our first example where force changes from spot to spot. Luckily, it changes in as simple a way possible. It changes linearly, but it does change from spot to spot. So how do we deal in physics with situations where the force is changing from spot to spot? Well, we invent or construct or discover this idea, this concept called work. Okay, I'm saying right. So I'm going to go to the next page. What I'm saying right here, again, this is the solution problem, but I'm now going to explain like the steps of this. I'm saying that work is defined to be the integral of force with respect to displacement. That's a definition. It means we're about to get into integrals now at some level. In okay. So I'm defining a thing called work. Work is force acting through space. Work is force acting through or along some displacement, some change in position along one axis, one axis of space. I'm not saying this is a discovery. I'm saying this is a definition. And now let me try to break down what this, so technically it's an integral, but what does that mean? Like, why is it an integral and what does that mean in regular English? What I'm saying is we can understand why it's an integral and what we mean by an integral if we first examine let's examine what this definition would mean in the limiting case of a very, very small displacement. I'll tell you what I mean by small in a moment, but just imagine a small yet finite displacement. Let's call that small but finite displacement delta x, okay? Instead of d, which technically means infinitesimal, right? Let's think of some small but finite displacement delta x. Over a small but finite displacement, approximately speaking, what a small amount of work, delta w, would be is force times that displacement. Like literally, if I push something with 3 newtons of force through a 2-meter displacement of space, we're going to say that the work done is 3 newtons times 2 meters, or whatever numbers I just said, 3 newtons times 2 meters of work. And work is going to be measured in units called joules. 1 joule of work is 1 newton of force times 1 meter of displacement. Okay, so in a simple case where we have just a small amount of displacement, the work that we do is however much force we're exerting throughout or multiplied by however much displacement we're undergoing. So if you push a box and you push it with 3 newtons of force and you displace that box 2 meters through space, we say you've done 6 joules of work. Work is, in other words, work is the product of interaction and result. It's how much you're interacting with something and how much that's resulting in a change in that thing's position. Okay. So if you're not pushing something at all, you're not doing any work. But if you're pushing it a lot but not getting anything done, like if you're just pushing against a wall, you're not doing any work. It's a product, it's multiplication, because the bigger either element is, the bigger the whole thing is. And if either element is 0, then the whole thing is 0. So it's multiplication. So in the simplest terms, in the simplest case, in the simplest scenario, when a displacement is small, work simply equals the product of force with displacement, the product of force times displacement. Well, what do I mean? By small, when I say, so I'm saying when displacements are small, work just means force times displacement. And we're just, again, it's just a definition. I haven't said yet what we do with that or why we care. I mean, we care because we're interested. Anyway, I haven't said what we do with it, but I'm just saying we define it that way. In simple cases where the displacement is small, work is just the product of force with displacement. Well, how small is small? Small is small enough to keep the force constant, like a small enough interval that there isn't enough room yet, or there isn't enough time yet for F to vary much. What we care about ultimately, though, is what about displacements that are big enough to allow F to start varying? If we're what I'm saying right here is ultimately the whole is equal to the sum of its parts. I'm saying work in the small case is defined to be force times displacement. And that's a no-brainer as long as force is just some number that doesn't change for that small displacement. We just multiply that number of newtons times that number of meters, and we have the work done. Once we're pushing something over a large displacement, like with this spring, once we're pushing things through a large displacement that's large enough for the force to start varying, how can we get the work then? Well, we can say the total amount of work done throughout an entire large space is the sum of all of the partial works. Like we could take some, and this may start sounding familiar to you from a math class. We could say if you want to know the total amount of work done over some interval that's so large that the force is different amounts at different pieces of that interval, just divide the whole space into lots and lots of little small spaces, each of which has its own little F that applies, and say, okay, the work done over this 100 meters is really the work done over the first meter, plus the work done over the second meter, plus the work done over the third meter, plus, et cetera, et cetera. Just divide up into segments that are small enough to each have their own little F that applies, and just add them all up, right? I mean, that makes the whole is equal to the sum of its parts. So we could say, in other words, a total amount of work equals the sum of all the small works. This is a big sigma, meaning sum, right? And more specifically, then the total amount of work done for some interval would equal right. And I'm starting to get a little fancy here. I'm not trying to intimidate anybody. I'm just trying to make a point. I'm just saying here that, like, if you had, if sorry, Yeah. I'm just saying, if you have this big, large displacement, you could divide it into lots and lots of small displacements, equal displacements, like divide 100 meters into 1 meter, second meter, third meter, and divide it into segments that are small enough that each one has its own constant little f. Just get the f times delta x for the first segment, put it in your bag, add that to the next f times delta x of the next segment, put it in your bag, and just keep adding up the f times delta x for all the small segments, and you'll have the f times delta x for the whole thing, right? Like, that makes sense. And that's true, and that's right. So the only thing I want to say now, and this might be familiar from math class, is like, okay, but for each segment, like how small, we have to make the segment small enough to each capture their own little constant f. In reality, okay, I know there's 2 more minutes, I'm just about done, but I'm not trying to assume that you understand everything about calculus right now or about energy. I'm actually trying to tell you how calculus works here. I never understood integrals until this context. What I'm saying is, we want to sum up all these little products of dependent variable f times independent variable delta x. We want to sum up all the little f times x products, but we want to sum up enough delta x's for which in each delta x, f doesn't vary at all, right? If f is varying continuously, like we can, the smaller and smaller we make each delta x, the closer and closer we'll get to capturing a steady f for each one. But we'll never perfectly capture this answer correctly. F will always vary a little bit as long as delta x is finite, if f is varying all the time continuously. So what we really want here is, we want the sum of all the f delta x products, but we want a continuous sum. We want the sum in the limit as delta x goes to 0. We don't want just finite small intervals of x. We want infinitesimally small. And I know we have 1 minute and I'm just about done. We want infinitesimal intervals of x. When you take delta x to the limit of 0 as it approaches 0, that's what we call dx. Dx is an infinitely small delta x. And when we take the sum over these infinitesimal small elements, we're now a smooth continuous sum instead of the discrete sum of sigma. We change that sigma to a smooth s for sum, and that's what an integral is. In other words, this is the last thing I'm writing, then we're going. Believe me, I know. We're going to stop right here. Okay, we are going to stop right here, but I just want to make clear to you. Work is the integral of force with respect to displacement. Integral just means continuous sum of force times displacement. This is what an integral is. It just means add up all the little products, but in the limit when add up all the rectangles when the width of each rectangle goes to 0. So we're going to stop right there. We'll get back to this more on Monday, but work is defined to be the integral of force with respect to displacement. That just means it's the product of force times displacement, even in cases where the force varies continuously as a function of displacement. An integral is just a smooth, continuous sum of products. That's what an integral is. That's what it is. And the most standard, classic, vivid illustration of an integral is the work integral. So we're going to leave it right there. I'll get back to how I use that to solve the problem. I'll get back to kinetic energy and potential and all that on Monday. Just keep going with whatever you can in the problems right now. Thank you I'm going to hang up for a second to answer any questions, but then I have another class coming in 4 minutes. But thank you very much. You've all been great. I'm done. I'm turning off the recording, but I'm here for a minute if there's any.